All righty. So we've talked about position. We've talked about speed and velocity, which is, in essence, how fast your position is changing. Well, guess what? Now we're going to talk about acceleration, which is how fast your velocity is changing. So, in your car, what shows you your acceleration? Okay, we've got the speedometer. Do we have an acceleratometer?
RPMs? No.
No, that's how fast your engine is spinning. If you have a needle for your speedometer, your acceleration is how fast the needle is moving up across the numbers. It's how fast in essence, your speed is changing. Which, think about it. If it if it's just gradually going from 10 to 15 to 20 miles per hour, that's a small acceleration. We know that physically. We know that. Whereas, if we've got, our Charger, Dodge Charger with, that monster Hemi in it, and you mash down on the acceleration and it goes from 0 to 60, in about 1.2 seconds or something like that. That's a whole lot more acceleration. And that needle went from 0 to 60 really fast, and you're shoved back into your seat. That's a lot of acceleration. So how fast your needle is moving or how fast the numbers are spinning up or down actually indicates your acceleration. All right. So since velocity is a vector and it has magnitude and direction, guess what? If either the magnitude or the direction is changing, you have acceleration. So you may be driving at a constant speed as you go around a curve, but your direction of your velocity vector is changing. So there's actually an acceleration involved. All righty. Here's a definition for acceleration. It's your change in velocity over time, which means your final velocity divided by or minus your initial velocity divided by time. Back to the charger at the stoplight. Changes green, you mash on the accelerator, right? Your initial velocity was 0, your final velocity would be 60 miles per hour, and it took you 1.2 seconds. We can figure out what the acceleration is. From a unit standpoint, it's velocity divided by time. And so in the metric system, velocity was meters per second. So we got to divide by seconds again. So it's meters per second, or some people write it as meters per second squared. Similarly, feet per second squared works. Yards per year squared. Parsecs per fortnight squared. I don't care. Any valid unit for distance divided by any valid unit for time squared is a valid unit for acceleration. Most of the time in the metric system, we see meters per second squared. In the US customary, feet per second squared, that kind of thing. But all the examples I've got on the screen are valid. They work. It's a velocity term, right, divided by time, or a distance term divided by time squared. It all works. All right, let's talk about example 9.3. We've got a ball falling. We're told initially it's falling at 20 feet per second. 0.3 of a second later, it's doing 11.6 feet per second. George, was there a change in velocity?
My mute button disappears. Yes, there was a change in velocity.
Okay, so there has to be an acceleration. Question is, what is the acceleration? We have this lovely little equation. We know the final velocity, 11.6. We know the initial velocity, 2. We know how long it takes, 0.3. So we can put all those numbers in there, bang on the calculator, and it turns out it's 32 feet per second squared. Which should look familiar. Joe, what is acting on this ball while it's falling?
Gravity?
Yeah. And in US customary units, the acceleration due to gravity is 32 feet per second squared. All right, here's a short, quick little video about acceleration in the space shuttle done by Dr. Weil. I'm going to let him chat with you for a bit.